Hi students, this is Madhu D. Welcome back to the Electrostatics lecture series. So in this video lecture, I am going to calculate electric potential due to uniformly charged solid sphere non-conducting like plastic. Uniformly charged solid sphere. Okay, we have calculated electric field due to uniformly charged solid sphere non-conducting already. If you have not watched that video lecture, I'll put that video link in the description column of this lecture. Please watch it because I am going to use the electric field values calculated there and I am going to use the relationship between electric field and electric potential to calculate electric potential. So here basically electric potential is calculated from electric field values using relationship between them. Okay, using relationship between them, remember. So electric potential, electrostatic potential is calculated from electric field using relation between them, that is E equal to minus dV by dr. So I am going to use this relation. Okay, so I am going to use this relation. So let me write it here somewhere. E equal to minus dV by dr. So I'm going to use this relation minus dV by dr. Okay, so I'm going to use this relation. Right. So before I calculate this, first let us see what is solid sphere, what is non-conducting, how charge is distributed. Right. So solid sphere non-conducting means a sphere throughout its volume material is there, which is made of plastic if it is non-conducting, and the entire charge that is given to this type of sphere is distributed uniformly over its volume. Right, so I'm considering a sphere, solid sphere non-conducting of radius capital R, so that if plus q charge is given to it, it is uniformly distributed over a volume of that sphere. Okay, and we have already calculated electric field values for this case. That's why I'm asking you to watch that video, because I'm going to use those values here and use this relationship. See, we have also seen done one video on this electric field and electrostatic potential relation, E equal to minus dV by dr. I will also provide that link. Do watch those two videos so that it will be easy for you to understand this lecture, because I am going to calculate V by the relation E equal to minus dV by dr, and for this E value I am going to use E values already calculated. This E inside for this distribution is this one, E out on surface for this distribution is this one, and E outside for this distribution is this one. Okay, so now I am going to calculate V outside, V surface, V inside by using these relations. Okay, so case 1. So case 1 is at a point outside. It is R greater than R. Means the point is somewhere here, and the distance of that point is smaller. Point is here, so V out. Okay, so this I am going to calculate now. So for that, we know that E out is equal to 1 by 4 pi epsilon naught q by r square, right? And from that relation I can write minus dv by dr is equal to 1 by 4 pi epsilon naught q by r square, right? So dv equal to minus 1 by 4 pi epsilon naught q by r square dr. See, here I am directly not writing v out because I am going to use the limits here to solve the integral. Okay, so dv equal to this one, and the limits integrate both sides by applying limits. But dv, what are the limits now? For the limits, what I am assuming is another test positive charge q naught or unit test positive charge is now brought from infinity to this particular point. See, this is charge distribution q, right? At infinity distance, let us assume one unit charge positive. So for this, the v infinity will be 0 because v infinity we assume it as 0, right? So that charge is now moved from infinity to this particular point. So that is r, smaller, right? So v infinity to v at this point is our v infinity is our difference here. Okay, so infinity to what, where the unit positive charge is moved, infinity to a particular distance. See, you have to calculate distance from this charge. So initially the unit test positive charge is at infinity and it is now coming to r, right? So that is why it is r. So minus 1 by 4 pi epsilon naught q by r square dr. Remember, for calculating outside electric potential, I am assuming a unit positive charge initially at infinity distance from this, so that v infinity is 0. Now that unit positive charge is assumed to be moved to this point, where the distance of that point is now r. So infinity to r. So v infinity to vr. Vr is nothing but v out. Okay, this is how I am calculating. Okay, so now what is this answer? So this is minus 1 by 4 pi epsilon naught. Q is constant, so infinity to r. So minus 1 by r square dr. Minus 1 by r square dr. Okay, so I'm going to solve that integral. So on the left side, what do we get? It is v infinity minus v out, right? So v out minus v infinity is equal to q by 4 pi epsilon naught, q by 4 pi epsilon naught 1 by r infinity to r, 1 by r infinity to r. Okay, so what is the answer for this? Q by 4 pi epsilon naught 1 by r minus 1 by infinity. So this is v out minus v infinity, since v infinity is 0. So in the next step we got v out as 1 by 4 pi epsilon naught q by r. So that is the answer for this electric potential at outside point. Electric potential, this is electric potential at outside point at a distance of r from the charge q. So this is how we calculate. Okay, so now we will calculate case 2 at a point on surface r equal to r. Okay, for this I don't need any integration, I just can replace the small r as capital R. We usually do that for calculating values on surface. So case 2, at a point on surface r equal to r, right? So V surface is equal to 1 by 4 pi epsilon naught q by r. It is simply direct. So in this equation, if we substitute r equal to r, we get this. Okay, so V out and V surface. Case 3 is very, very important. It is going to be little complicated, right? So for this case, case 2 case, point is here and distance is here, r equal to r. For case 2. Okay, so now we will see case 3. So this is, you can say, electric potential. This is electric potential at a point on surface. At a point on surface. Okay. We'll see case 3. Very important. Case 3 is very, very important. At a point inside r less than r. At a point inside r less than r, and we know that E inside is equal to 1 by 4 pi epsilon naught q by r cube r. This one proportional to r. So this time our point is now not on surface. Our point is well inside r less than r. Okay. So using this relation, minus dv by dr is equal to 1 by 4 pi epsilon naught q by r cube r, and dv equal to minus 1 by 4 pi epsilon naught q by r cube r, right? And integrating both sides by applying limits. Integrating both sides by applying limits, right? So what are the limits now? So for example, consider a charge q naught, sorry, a unit positive charge is on the surface initially, and it is now moved to point P, well inside, in the electric field produced by this Q. Okay, so our now reference is Vs, V surface, right? And the distance is now the charge that is moving from capital R to small r. Capital R to small r. So this is how we dV. This is V surface to V inside is equal to V surface is at a distance of what? R, capital R. V inside is at a distance of what? Small r, right? So minus 1 by 4 pi epsilon naught q by r cube into small r. So this is equal to minus 1 by 4 pi epsilon naught q by r cube is constant. We got r to r small r dr. See this here, it is r is there. R is there. So r dr. Okay, now we have to solve this integral. What is the value of this integral? See, on the left side we have V surface to V inside is equal to, on the right side we have minus 1 by 4 pi epsilon naught q by r cube constant, and that value is r square by 2, this one. R value is, integral r is r square by 2. Okay, so now we will apply these limits and see what is the answer. right? So here V inside minus V surface on the left side is equal to minus 1 by 4 pi epsilon naught q by r cube into small r square by 2 minus capital R square by 2. Okay, right. So we know that V surface is equal to V surface is equal to 1 by 4 pi epsilon naught q by r. Substitute this here. So V inside is equal to this side. So 1 by 4 pi epsilon naught q by r. This as it is minus 1 by 4 pi epsilon naught multiply inside. So r square by 2r cube and plus 1 by 4 pi epsilon naught q by 2r. See r cube, r square cancels with this cube, so 2r. Okay, be careful while doing this calculation. So out of this, I can take 1 by 4 pi epsilon naught q by r as common. So that here I will get 1, and this here I will get plus 1 by 2, and next here minus 1 by 4 pi epsilon naught. See here q is there, that's why I'm saying it, be careful. So 1 by 4 pi epsilon naught q by r is common, so r square by 2r, r square by 2r. Okay, r cube, right? So 2r cube, so 1r is r square by 2r square, you can say, because q into r square by 2r cube it is. R square by 2r square. Okay, so this is nothing but V inside is equal to 1 by 4 pi epsilon naught q by r 3 by 2 minus r square by 2r square. So this is V inside. This is electric potential at an inside point. At an inside point. Okay, and from this we can write one special case that let me take out this. One special case I can write. Right, at center of sphere, small r equal to 0. So V inside is equal to, that means V center is equal to how much? Small r equal to 0. So 1 by 4 pi epsilon naught q by r into 3 by 2, which means that is, you can say that is 3 by 2 times, or I can say 1.5 times, that is 3 by 2 is 1.5 times, 1.5 times electric potential on surface, because V surface is equal to 1 by 4 pi epsilon naught q by r. That means V center is equal to 1.5 into V surface. So 3 by 2 is 1.5 and this is V surface. This is very, very important for entrance exam. At the center, the value of electric potential is 1.5 times the value of electric potential on the surface. It is very important. So now we have calculated, this is case 3. Till now what we have discussed is case 3. Okay, so now let us write all these values at one point, at one place, right? So V outside is equal to 1 by 4 pi epsilon naught Q by R. V surface is equal to 1 by 4 pi epsilon naught Q by R. And V inside is little interesting. That is this 1 by 4 pi epsilon naught Q by R times 3 by 2 minus R square by 2R square. Right? So the graph for this will be like this. This is R, this is V. Right? So it will be like you can say this. It will go like this and like this. So for this point, you can say this is R and this is center. This is center of the sphere. The center of the sphere is VC. This is V center is equal to 3 by 2 times 1 by 4 pi epsilon naught Q by R. 3 by 2 times 1 by epsilon 3 by R. And this is V surface 1 by 4 pi epsilon naught Q by R. This is R. See, at center it is 3 by 2 times surface. And on the surface it is equal to this. And as you go away from the surface, this is this one. From this point, it is like this. Make it one line. This way. Okay, so very, very important. Hope you have understood. If you have any doubts regarding this lecture, you can put your doubts under the comment section. Thank you very much.